Hello everybody, it's a great pleasure to give a talk today, and I try to introduce venture to ion platform and some ion computation, so maybe it will be interesting for some of you considering address students, of course, mostly, to contribute to this field and to think about this technology, basically, which is very active today. So these issues every one of you already know, I'm sure. So generally, the quantum computation is based on superposition, entanglement, and quantum parallelism, which allows to solve several, or it's assumed to be more powerful compared to regular computers in sense of factorization, searching of databases, and design of new materials depending on what one wants. If we restrict our Hilbert space by atoms and ions, which are natural qubits, so you do not have to synthesize them to design it by some way. So we end up with ions and neutral atoms. They are, from some point of view, they are very similar because their levels which you use for quantum computation are generally the same. We will see either electronic states or some other internal states, but the difference is how two species, how two ions or two atoms interact with each other, because ions have strong interaction between each other because of Coulomb force. It's a strong force, and it scales as 1 over r squared, so it's a really strong one. If you take two neutral atoms, which you can of course have many of them, if they're in ground state, the interaction scales as 1 over r to the 6th power because of van der Waals interaction. And of course, there are two different situations. So here you have to excite to Rydberg states and do some special manipulation with neutrals. With ions, it's a little bit different world, considering how you prepare the sample and how you work with it. If you summarize today's progress idea in some sense to, maybe it's not up to date because everything changes very, very promptly, we see that ions maybe are not the most powerful platform in the sense of number of qubits, because it's one branch. You have to increase the number of qubits to have more and more powerful system. So today it's 53 qubits for simulators and only 11, today it's 13, I think, already reported qubits for quantum universal computer. Okay, compared to other platforms, it looks more or less the same. Coherent time is quite outstanding for ions, so you can find levels which have coherence times up to several minutes. It's fantastic in some sense. The gate time is also, it can be quite fast. There is a trade-off which we will discuss later between gate time and fidelity, but it's still around few microseconds. And what is interesting is the fidelity of operation. It's much closer to 1 compared to other platforms today, which allows to do some interesting things concerning universal computation, even using small number of qubits. There is a problem. We will discuss it in a few slides later. That it's very difficult to scale the number of qubits in this system, but that makes things interesting because there is a problem. General approach to, we will again look at this level structure a little bit later, just to understand why there are some additional levels besides the electronic levels. But the general idea is that you take a chain of ions. It's generally the chain of oscillators in some sense. So the easiest way to think about ions is to think about some masses and spring between them, because it's really a good oscillator in some sense. And then you excite one of the ions, not only the electronic state but also vibrational state. Then you entangle ions using this operation. They start vibrating as a common structure. And I'm too fast. And then you do reverse projection, and you can make entanglement of two electronic states of ions in the chain, and return back to the no vibrational state. So this is a general approach how most of quantum algorithms using ions work. But then we have to go into a little bit details. Okay, there is a historical part, which the first part is well known for all platforms. Then 1994, Zoller and Sirac suggest first physical realization of ion quantum operations. It was on paper. Then in 1995, Chris Monroe and Dave Vineland demonstrate first 2-qubit operation using beryllium plus ion. In, I think, 2001 in Innsbruck, the group of Reineblatt, it was the first CNOT gate demonstrated using calcium ions. Then 2006, first chip trap, which is not yet a leading platform, but it's still interesting that it works. 2009, first universal programmable 2-qubit computer. Then 2012, well-known Nobel Prize for manipulation with single ions to Dave Vineland. And then we see the progress, 5-qubit, 11-qubit, and I hope that it will go further in some sense. So if we go inside this story and we look in ion, what we will see, there are several states which can be used for computation. Of course, it's electronic states, it's optical transitions, which is about 100 terahertz. There are lasers which are needed to excite these transitions, typically very narrow band lasers. For example, calcium ion use optical transition. There are also well established hyperfine qubits, so the qubits which work on hyperfine states with an energy separation of about 10 gigahertz. And for example, ytterbium ion is qubit in ytterbium ion works in this configuration. One can also think about Zeeman's structure, but it's less, less advanced today. There are motional states, which we will again look a little bit later, which we have to add electronic states and motional states of ion to get the full picture. The procedure is quite typical. If we talk about computation, we have to trap ions in some trap, which we will discuss in one slide. We have to Doppler cool it, which is used. It's very similar to laser cooling of neutral atoms. We do ground state cooling, which is different from neutral atoms. Then we do quantum state preparation. Then we do some operations. And then we have to do readout. If we go into details, of course, okay. Now what I would like to deliver to you in the first part of the lecture is how this, physics works, how the trapping works, how cooling works, how state readout works, how quantum state preparation works. And then maybe, if I'm clear enough, I will give you some general picture of ion-based platform for computing. So, okay, let's start from the very beginning. Year 1989, the Nobel Prize to Wolfgang Paul for trapping ions. It's much earlier than Nobel Prize for trapping neutral atoms. You see, the trap itself was developed much earlier. Their idea is relatively straightforward. It bases on the fact, okay, you cannot configure static electric fields or static magnetic fields to trap single charged particle because of Earnshaw theorem. So there is no way. But there is no prohibition to trap or localize particle using alternative fields, so like DC electric field, AC electric fields. So if we write a Laplace theorem for the space which is free of charges, assuming the parabolic potential, for example, in three-dimensional situation, it's our space, then there are two solutions. First solution on alpha, beta, and gamma. So okay, they have to be the sum of them have to be equal to 0, and you end up with two typical configurations. Either it's a 3D or volume trap where alpha equals to 1, beta equals to 1, and gamma equals to -2. So this is this case, which we will not consider in this discussion. Or you have the situation that alpha equals to 1, gamma equals to -1, and beta equals to 0, and we end up with a linear configuration, so-called the linear Paul trap. This is the configuration which is widely used for trapping ions for our purpose. The operation principle is can be described in this slide. So we have generally there are 4 rods. Okay, rod is a approximation of hyperbolic electrode, but hyperbolic electrode is hard to design, and there is no real optical access to the center of the trap, which is necessary. So, but round rods are good approximation for this trap, and many groups work with this trap. So it's good for modeling. 2 of these rods are grounded, and 2 of that rods are under radio frequency potential, which is very straightforward. So it's some DC potential plus sinusoidal potential, which alternates. Generally, you end up with a situation that the ion is in some saddle potential. So it's saddle potential which rotates around the z-axis, and from the first point of view, of course, there is no way to trap it, because if you have a saddle and you have the real saddle for a horse, you put a tennis ball in the saddle and you start rotate the saddle, you will not trap the ball, so it will not work. So you will lose the ball immediately. So there is a trick that there's some so-called pseudo potential which starts building up because of the fact that oscillations of the free particle is not in phase with the field, with external field. If you put electron and external field, it will oscillate in reverse phase with a shift of pi to external field. And then after some relatively trivial calculations, you end up with a so-called pseudo-potential. So it's a potential well, also parabolic potential well, which depth depends on the radio frequency voltage on electrodes. It depends on the distance between electrodes, so it should be also one of the reasons to make them closer, and mass of the ion and some other parameters. So generally, trap depth is about 1 electron volt, which is huge. So if we talk about temperatures, so when we work with neutral atoms, temperatures are typically millikelvin, microkelvin, and so on. But here, one electron volt it's 10,000 Kelvin generally. So we can really trap very, very hot particles from electron beams from different sources. And their motion in this trap can be split in micromotion, so it oscillations in frequency of excitation field, so in this radio frequency field. It's macromotion, which is a circular frequency, which is the frequency in this pseudopotential, and also oscillations along the z-axis, which is also necessary to confine the ions. So we trap them in this direction in y and x direction using this radio frequency trap, and in z direction we need to make some trick. We just apply, say, positive potential on these side electrodes. We have a grounded central electrode, and then we have the potential well in z-axis, so ion oscillates between this basically two walls of potential well. If we think a bit deeper in this situation, it's nothing special, which is really it's just for information. So it's their equations of motion of ion are not very straightforward, because there is a parameter which depends on time in this. At the first glance, it's equation for regular oscillator, but you have the coefficient which depends on time, but periodically. This equation calls a Mathieu equation, and it can be solved analytically. And then we have a quite restricted area of parameters which depend on this dimensionless parameters R and Q, which depend on trap parameters, radius, frequency, mass of particle, charge of particle, and the voltage. And if we are inside this area, we have a stable trapping of particle. If we are outside this area, we have not stable trapping of particle. And this is the reason why these traps can be used as mass spectrometers. So I would say that in Russia, for some strange reasons, I cannot explain it honestly, because we see that the Nobel Prize was given in about 30 years ago, but there were no ion traps in Russia for research over many years. We built mass spectrometers, of course, because it has very strong applied reasons and sense, but for research, for some reasons, people were not interested in this for very long time. Okay, axial confinement can be done by a few techniques. Either there are rings with positive voltage for example, if we want to trap positive particle, positively charged particle, or there are some rods which are split in parts, or there are some end caps. So generally, it's not important how you do axial confinement. We add interaction with radiation, so we have a trapped ion which is already undergo the electromagnetic force because of the electromagnetic field. So we see that there is a part which depends on time and on our radio frequency. We add the interaction with so it's internal state of the ion. Okay, we consider it as a two-level system for simplicity, and then we add interaction with for example, external radiation, which excites this two-level system. Generally, the Hamiltonian, which we write here, it starts to be quite complex. So if you straightforwardly want to solve it, it's not so very easy. But there are some lucky approximation, which is good for us because we work in this approximation typically. It's the combination of so-called Lamb-Dickey regime. Lamb-Dickey regime means that the volume where the particle is localized is much smaller than or comparable with the wavelength of radiation. So if we confine the particle in a box of the size of a wavelength, we call it Lamb-Dickey regime, and then we get rid, for example, of Doppler broadening. So it's interesting feature, for example. And we also assume that we have low anharmonicity of our trap, and then after solving this Hamiltonian, this equation, Schrödinger equation, basically, we end up with a relatively straightforward situation that there are set of course, our electronic states, so ground state and electronic state. So generally, they are our two-level system. We have vibrational states, which are the vibrational states in the trap. So we see it's regular oscillator, so it's quantum system, and it has vibrational states. And we have radiation, which couples these two states. And the highest probability in this approximation will be for transitions from the same, which couples the same vibrational number, so from n to n. So this probability is P0, it's denoted here. And all other branches have much smaller probability. So they can be coupled, but with a probability which is defined by this Lamb-Dickey factor, which is given generally by this expression. So the smaller this eta, the smaller the ratio, the branching ratio to this other vibrational sidebands. So if we go further and we think about manipulation with single ions and their states, we have to distinguish between resolved and unresolved sideband regime. So if we assume that this transition, this electronic transition is very narrow, it's not always true. We give the scales that you see the typical strong coupled transitions in ions. They are like 10 megahertz, 30 megahertz, 50 megahertz, which is not very narrow. So in rubidium, for example, the resonance transition is 6 megahertz. So here it's typically broader. The separation between vibrational levels in our potential is about 1 megahertz. So you see that in principle, this resolved sideband regime is quite unique. You really have to find very narrow transition, which couples electronic states of ground and upper state. For example, some forbidden transition, quadrupole transition, or something like that. And then you work in resolved sideband regime, and you can address basically each particular sideband of either ground state or excited state. If you work in unresolved sideband regime, so it's very close to what we have in regular situation in optical trap for neutral atoms. So we can do Doppler cooling, but we cannot go further in this case. So there are two quite different regimes, and we should think about that. Okay, we trap ions in Paul trap. Okay, I have to mention that there's not the single trap where you can trap ions. You can also trap ions in penning trap, but it's not for this purpose. So penning trap is combination of magnetic field and radio frequency field. So this is magnetic field and and DC field. So it's much more. It's different trap, typically cryogenic, and it's out of scope, just for information. So we trap ions. Typically they're at the temperature of a fraction of electron volts, so it's thousandth of Kelvin, and you cannot work with them typically. So because they move with velocities over 1,000 of meters per second, and you cannot image them, it's not so much interesting. You have to cool them. So very similar again to neutral atoms, you have to cool ions. How to do it? I will not go into details because it's today very straightforward and common technique. You do Doppler cooling, so you take a laser which is red detuned from a strong resonance. You illuminate ions and just wait. Then because of a Doppler shift, you convert kinetic energy into excess energy of spontaneous photon, and you go down and down in temperature. Then you reach the balance between the heating because of spontaneous emission and cooling, and typically you end up with the temperatures of 3 millikelvin. The advantage of ions in this case, it's not very prominent, but it still exists compared to neutral atoms, is that you can illuminate ion chain from one side. So you have not have this 6 beams and have the very symmetrical configuration, because your ion is already trapped. So you do not need to pay too much attention to how you cool it. But of course, this cooling beam have to be not orthogonal to some vibrational mode. So it have to be, so typically people still use 2 beams. So not 6, but 2. Okay, at the end you end up with a ensemble of cooled atoms which start to build a so-called Wigner crystal. So the Coulomb interaction is already strong enough. It's very prominent at this temperature and temperatures, and combining the Coulomb repulsion and confining potential, you either end up with some cloud of ions, which looks like that, or with some chain of ions. If it's linear trap, it looks like that, or with a single ion, depending on what you want. So it depends on the task. Today, about 20 ion species are directly laser cooled. So beryllium, magnesium, strontium, ytterbium, mercury, there are a few of them. Typically depends on available lasers for cooling transition. So it's nothing really special, because generally you can trap any ion in a trap you want. To measure temperature, there are different approaches. Of course, it's always discussable whether one can talk about the temperature for single ion, because it's not an ensemble. So temperature is a feature of ensemble. People agreed to think about temperature as kT over 3 kT over 2, or like a relation between energy and temperature. So this is, for example, the setup at Lebedev Institute, and we see that we can trap either a huge cloud of ions which are not resolved, they're really hot there, or to have a smaller cloud of ion, or to have like 11 ions in a chain or 1 ion, and then by spectroscopy measurement one can I will not go to the details, make the temperature measurement just to evaluate which is the temperature of this pieces, and they are like 10 millikelvin. Here it's 40 millikelvin, but this is the case. So they're still quite hot compared to neutrals, but sometimes it's enough. There is another interesting approach to manipulate with ions, is so-called sympathetic cooling, which also works partly in neutrals, but for ions it's even more prominent. For example, this is one of the very last, and I like this paper, which is published by PTB colleagues in Nature very recently. They trapped argon 13 plus ion, which is already not so tricky, which is tricky. But then they also cooled them by beryllium. So the thing is that you have ionic species, and if you have hot ion and cold ions of, for beryllium, then these common vibrations, the thermalization will take place, and of course, if you start cooling one part of the ensemble, another part of the ensemble will be cooled down as well. And you see that this argon is inside, so of course you cannot see it because it doesn't scatter photons. It's in this chain, and you can reduce the number of beryllium ions, and then you can leave with 2 species, and at the end they do very nice quantum protocol to read out the quantum states of argon 13 plus, very similar to what I will explain later. So basically you can cool any ion using sympathetic technique, and today, for example, it's also interesting to mention, people think about cooling sympathetically antimatter. So we know that there is a hydrogen minus ion, so we all know about hydrogen minus, which means that there exists hydrogen bar plus ion, which can be sympathetically cooled. So this is interesting. So people can do a lot of tricks with it. If one wants to go down in temperature, so 3 millikelvin is good, but for some quantum protocols you have to really go to the ground vibrational state. How to work, how to go there. In some sense it's quite straightforward. So you take a laser, you take it's suggested by, again, I think Vineland quite long ago. You take a red detuned sideband. So if you take a sideband for vibrational states, and you illuminate your ensemble by this radiation from one side. And then you will absorb this red detuned radiation, and after spontaneous decay, and we agreed that the vibrational number is basically the same. Then you will lose you will lose the vibrational quantum because of this process. And using this approach, you can or vice versa. I'm sorry. So no, it's true. So you have to go to red vibrational state, and then after many cycles of this process, you can go down in this ladder to basically ground vibrational state, which manifests itself using this, for example, spectroscopy. So you see that there basically red sideband is not presented anymore, so which means that there is no population on this level, and blue sideband is quite strong, which means that most of population sits on the ground state. Typically, the problem for this approach is that it's hard to find narrow and quite still narrow from one hand side, because you need a resolved sideband regime, but at the other hand side you need relatively prompt spontaneous decay to go with this process. Separation of vibrational states about 1 megahertz. You need a transition which is about 100 kilohertz, and it's tricky. So not many ions have these transitions. What to do? People work with Raman transitions, because ground state levels typically have very long lifetime. It's a good qubit. It's everything is fine. For example, if you take hyperfine structure or Zeeman sublevels, and no one prevents to do the same tricks which I showed you in the previous slide, using Raman transition by, for example, frequency modulated laser radiation, which is off resonance with some excited state to prevent spontaneous or strong spontaneous decay. So this works very good, and people already use it as a turnkey system. So you trap ions, you switch on the laser, and in fractions of seconds, you have ground state cooled ion if you neglect heating mechanisms. Of course, these heating mechanisms, they are tricky and nasty, and this is one of the handicaps towards well performance of quantum computation, because if I take ion and approach the surface, it can be gold-plated surface, it can be superconducting surface. For some reasons, there is some additional heating. So people do not understand very well where this heating comes from, but there is additional heating which comes from the surface. Either it's patch charges or some induced charges. People really do not know physics or understand clearly the physics which is behind it, but it's an effect, and it scales quite nasty with the distance to the surface, and the level which is acceptable is about 1 phonon per second. So it means that 1 vibrational quanta per second could be better, but it's enough to do reasonable things, I would say. And this is very strong limitation in some sense, because for many purposes and reasons, it would be nice to have ions very close to the surface. Okay. Anyway, one can go quite low with vibrational states. If we rely on calculations, we can go to fractions of vibrational state using different nice techniques like EIT cooling or double EIT cooling, or basically all of them are Raman cooling mechanisms, and people do it, and it works in different type of traps quite well. Okay, so we cooled ions. So now we know that we can cool ion to the base ground state, both in electronic structure and in vibrational structure. So we have a potential well, and we have the ion in the ground state. What then? if we think about 2-qubit operation, of course, because 1 qubit is not interesting generally to anyone, we have to entangle by some way a few ions or a few particles. Yeah, so this is a key issue for all quantum computation tasks. How it works? Sirac and Sola suggested to use the common vibrational mode. So if you have 2 particles or 3 or 5 particles in a trap and you excite vibration, they all will move together. So this will be a common quantum state because it's already quantized, so it will be a common quantum state. Of course, the situation is, again, okay, it's for 2 ions it's very straightforward because you have either center of mass mode where when 2 ions move that way in the potential, or it has stretch mode where they are moving that way. So there are only 2 modes. If we go to 3 ions, we have 3 modes, 5 ions, 5 modes, 100 of ions, it's 100 modes. So, and all of them have a little bit different frequencies, but they're more and more dense. Of course, there are also other dimensions, and ions can move in other planes, but this is undesirable, I would say, in some sense. If we look, it really looks like an oscillator. So it's a first year student task how to excite 1 or 2 oscillators. So we have an ion. This is our experiment, for example. We apply some force, for example, by modulation the radio frequency or modulation of laser beam. It doesn't matter. We shake the ion and we see that at some certain frequencies it's resonance. So 1 ion have very nice resonance, and it looks like here, like that. 2 ions, they have 2 resonances. We also can measure them, either that this mode or this mode. It's hard to distinguish, but generally it looks like that. And we did some experiments, and we see that we can excite these vibrational modes. They have very different frequencies. It's 51 kilohertz, for example, and 91 kilohertz. It's really easy to tune to certain vibrational frequency. But if you increase the number of ions, there are 2 issues which you have to consider. Because of course everyone wants to have not 2 qubits, but I don't know, 100 qubits, for example. If we increase number of ions, it works. First, we see that one can trap 1, 2, 3, 5, and we can do basically the same at our experimental setup. But in addition, we increase the number of modes, of vibrational modes. This is number of ions. This is the frequency of certain vibrational mode, and we see that they become more and more complicated structure. Typically, the common mode, which is typically used for quantum computation, is well separated. You see that it's still quite separated, but the situation becomes more and more complicated, and it's harder and harder to address this common mode. Another issue, which is today, I think it's the strongest difficulty in the whole history of quantum computing using ions, is the scalability. Because if we start to increase the number of ions in the chain, how to do it? Typically, we make potential more and more soft. So z-axis, so we just reduce the voltage on n caps, for example. And then we trap more and more and more atoms. It looks nice till some moment when they start to build a zigzag configuration, because they are not well localized, and they start to make some zigzag. Of course, all the story with the vibrational modes becomes different, and situation changes, and situation becomes much more complicated, and people cannot work with it typically. So one have to work with linear chains of ions if one wants today to do some reasonable computing. The number of ions which is more or less robustly can be trapped today is about 20. So 20 ions can be put in a chain, and it's reproducible, and you can work with them. Okay, the last instrument which we need is a state readout. So because we prepared ions, they are two-level systems. We can do many things, many nice things with these ions, of course. But then we also have to know at which quantum state this ion is at a certain moment. So we have to project the wave function on certain basis. This is done quite straightforwardly. It's not easy, but straightforwardly. It's done by the method of quantum jumps, typically. So we have, for example, our clock transition or qubit or whatever you want. So this is some transition which could be superposition between S and D state, for example. And then we applied a strong electromagnetic field which couple ground state to some dipole allowed transition, for example, to P state. So we excite 10 million transitions per second, for example. So it's about 10 to the 6 scattering rate. Of course, if the system is in a ground state, we emit about 10 to the 7 photons per second, which are easy to detect. So, and then we can put some optics and just see whether the ion is shining on our CD camera or not. Of course, this procedure is just a projection of the superposition of this wave function, which can be superposition of S and D state, for example, on our basis. So this is a typical approach. One can, of course, do it with a chain of ions. One can do it simultaneously. So it's not a very difficult technology. And here it's an example of one ion, for example, when one of the transitions, so clock transition, is excited, and this projection took place, and you see either you see ion or not see, depending on in which state it occurs after projection. So this approach is also well known and widely used. Okay, how it works in hardware? Typically they are quite compact setups, so they are not very bulky. So the vacuum chamber which you need, so I mean the tool, the Lego tool which you need if you want to build a ion trap. So it's a vacuum chamber with a pressure of about 10 to the minus 10. It's straightforward today. It's more or less easy. You need some money, but it's not difficult. You need a source of your ions, not ions, your neutral atoms. So if it's a terbium, then it's metal terbium. If it's magnesium, it's metal magnesium, whatever you want. Then you have the rods and the trap configuration, either it's blade trap or rod trap or again whatever you want. Some electrodes and wires and cables which go outside to apply the radio frequency field, and you need really good optical access to the center of the trap, because everything else which you need are laser beams. So for example, if you want to produce ions inside the trap, you need a photoionization. So it's photoionization laser which ionizes neutral atoms, and you trap ions inside the trap. You can do it also with electron gun, which we did long ago, but electron gun, it charges everything around, and these PET charges, they are not good for high precision experiments, I would say. This is the real trap which you see here. So it's basically the implementation of the previous picture. So there are the rods, some wires, and channel electron multipliers, which we used long ago again for counting ions. But generally that's all. So it doesn't look very complicated. If you do not want to think about this very low heating rates, because if you go to really low heating rates, you need quite to think about what you put inside. Because if you go in YouTube generally and trapping charged particles, you can find them basically using any piece of wire. I can trap the charged particle. So it's not really difficult to trap a charged particle. So this is true. Okay, this is the picture of the ions which we have inside this trap and so on. Okay, let's go now. So we have all instruments assembled together to do something reasonable for quantum computation. And indeed, the first two-gate proposal was given by Chirac and Sola, two theoreticians, one from Max Planck Institute of Quantum Physics, another one from Innsbruck University those times. And the idea is to implement the CNOT gate, which is universal gate, using two ions which share vibrational states. So I will not go in this picture in details because we go through this protocol in more details in a few slides. So the general idea is to implement a CNOT gate, so true CNOT gate, which is universal gate. If you have CNOT gate, you can have any quantum algorithm you want. So that's good. And how to implement it was proposed by these two guys. Let's go in a bit details because this is a very good protocol for teaching. So it's not today, how to say, implemented widely because it's slow and it needs cooling to ground vibrational state, but it's very good to understand how it works. So we need two ions. Okay, two ions are there. We need common motion, which it's also a state which we can excite. It can be 1, 2, 0, 1, 2, 0, 1, 2, blah, blah, blah. And we can some operations which can be done by optical fields. So we can manipulate the states with Rabi pulses from outside the chamber. Okay, let's remember, and it will give us a little bit situation a little bit simplified, that CNOT gate and phase gate are generally, in some sense, are very close because from phase gate, which looks like that, so generally it's additional phase on this part of the matrix. You can translate phase gate to CNOT gate by implementation of two pairs of Adamar gates, which is really straightforward. So I wouldn't like to go into details. It's today even straightforward using any computing, any software and hardware, both Josephson and neutrals and ions. So this is 1 qubit operation. So it's not difficult. So basically, what I would like to say that if we can implement the phase gate, it means that we can implement CNOT gate by very simple transformation. Okay, let's also remember because it goes into protocol, and it's interesting to mention that what does 2p pulse on a quantum system, because naively one can think that if we have the Bloch sphere and for example, we have this system which, for example, in some state, some ground state, and we do 2p pulse on a Bloch sphere, nothing changes. So we take a population and we transfer this population through 2 pi. But it's not true because if we look at the expression for wave function for spin 1/2 system, we will see that during this operation, we gain a phase we gain additional phase, and the state will change to minus state. So we will basically change the sign of the state by using, for example, 2p pulse on one of the states. This is true. That can be explained by different ways, but from Wikipedia you can see these expressions. It's easy. Okay, which means that if we take, for example, the system which consists of ground state, excited state, and vibrational state, so the right part is the vibrational state of our system, we will see that if we apply 2p pulse, we will get minus at this part, because if we have some population in this state, it will gain the sign minus. All other states, this state is untouched, this state is untouched because there is no coupling level to this. This state is also not perturbed because we have a red sideband, and we do not have any level here. So we just manipulate with one of the states using this 2-pi rotation. Similar to say, well, if we apply the same algorithm for pi rotation, we will put some I either here or here, depending of sign of pi pulse. Okay, now let's go to the composition of Dirac-Sola operation. It consists of basically 3 parts, and we start from initial state. So we have control bit, we have target qubit, control, target, and the motional state. So we have generally 3 parts of a wave function: control, target, and vibrational state. We have all these 4 states prepared, everything is fine, population is somehow distributed between levels of control and target qubit. So this is psi 0, everything is fine, we need 2 ions to start this operation. The first, what we have to do is to transfer the population of control qubit, or to map it to the ground state, but not to the true ground state, but the first excited level, so vibrational level of the ground state. So we make this transfer by applying a pi pulse, so a light pulse with a certain duration and intensity. We end up with the situation that we excite the common vibrational state, so it's from 1 to 0, from 1 to 0, it's okay, it's common vibrational state, it's very important. And we have this minus I at the beginning, which is mentioned earlier. Okay, good. This is the next, psi 1. Then we go to psi 2. So next step, we take this. It's very important. This may be the most important part in the whole algorithm. We take some auxiliary level and we apply 2p pulse on this target qubit first vibrational level. And we change the sign of only one part of these 4 guys. So this changes from minus I to plus I. Good. So we accumulate some additional phase. Please remember that we accumulate some additional phase which is needed, and that will be used for other protocols which we will discuss a bit later. Okay, that we had added this phase. Then we go to the last step. It's psi 3. We again apply pi pulse. So basically, we return this population back to the excited level. So we reconstruct the control qubit. We do not touch the target qubit. We take the vibrational vibration from the system. So because we would like to return it back to non-vibrating state. And what we see at the end, that we see everything basically like at the beginning, but with a sign minus at the last part. Generally, that's all because we implemented the phase gate. So the whole story is ended by generally 3 pulses of light for this system. Of course, if we want to go to CNOT gate, we need some additional tricks, but they are straightforward. But we get the phase gate using Dirac-Sola gate. What is good? What is bad? So good is that it works. So it works. It was demonstrated more than 10 years ago. Fidelity of this gate also exceeded 99.9%, and it looks fine. Besides the fact that it's slow. First, it's slow, and second, it needs to have ions in true ground state. So everything should be cooled in ground state. And of course, if we go to the practice, how it works. So we have, for example, 2 ions which are in ground state. We do some manipulations with them. We maybe perfect manipulations, but we have some heating. So we have some heating because the surface, radio frequency and so on, it heats ions, and at some moment they start to vibrate. It it's bad because we lose information, and we make fidelity of the system poorer, and basically we ruin the protocol at some moment. So what you need is regularly cool ion to the ground state. You have to interrupt the protocol, cool ion. You have to interrupt the protocol, you have to cool ions. So it's a bit tricky, or you have to have some another ion which will sympathetically cool the whole chain, which is also not so straightforward, because this additional ion doesn't help the situation drastically. So is it possible to do something different? So here are the limitations. So Sirac-Sola gate requires well-prepared ground state, and it's so-called adiabatic gate. So it means that we need the time for this gate which is comparable or larger than the typical oscillation time of two ions. The question is whether it's possible to make this phase acquisition. So we need some we have two ions generally, yeah, so it's hard with microphone. We have two ions, and what we need? We need some operation which makes additional phase on this ion depending on state of this ion. So it can be done because depending on, for example, distance of, we know, for example, if we have ground state and excited state, we can have different polarizability of two states. So it can be differently. So there, I hope most people know what is polarizability. So there, if you take an ion or neutral atom in external potential in electric field, then it starts it's polarized, and it's some force between the atom and external field, for example. So the ratio between the level shift and the electric force, electric field is a polarizability. It's alpha. It's coefficient which reflects this polarizability, and if you have the level shift, it means that it's additional phase added to the system. So, for example, if you have an atom, you add electric field, external electric field. Due to this basically Stark effect, so it's regular DC Stark effect, you add some additional phase to the system. So this can be used by different methods, and this is generally what we needed. So to use a Stark effect to state dependently add the phase to the system. So if we think about free oscillations on a phase diagram, so it's a regular picture of coherent state, and nu is the mode frequency. Of course, we can go to the coherent state in the rotating frame, and that we will see that it's just a circle at this axis. If we think about driven motion of a system with a frequency tuned from the resonance frequency a little bit, so we have some bit node. We have the force which is dependent on the state of the system, because what I explained a little bit earlier, and maybe it's not so very clear from this slide because it needs a little bit more details to explain, but generally you end up that polarizability of the system, it will be time dependent because we have some beating nodes between internal frequency of the system and applied frequency, so there's some detuning, and this will be state dependent. The important issue that it's state dependent, which means that if we do some manipulation with this two-level system, we will gain some additional phase. So this red circle, which is denoted here, and the additional phase is given by the force, by the detuning. It can be gained by manipulation on this system. So what we need? So generally we need to reach a pi. So very similar to what we had in Dirac-Zoller gate. Our goal is to have a pi equivalent of this circle. This can be tricky because there's competition. From one hand side, you have to be close to the resonance because then you get more phase. You have a large force amplitude. It's desirable to have a large force amplitude to increase the phase. But at another hand, one of the issues that you want to make this procedure fast. So and to make it fast, it's scales with a difference of frequencies, and it's better to be far from resonance. So you see the contradiction, so close to resonance, far from resonance. So is it some possibility to manipulate with the system faster than the common vibrational frequency? The answer is yes, and generally if we think that we can forget about this ground state cooling at the moment. So generally we have the force which is state dependent. So this force is state dependent. So it can be, for example, let's say spin down, spin up. It depends on the number of number of ions, because it can be quite many of them. This is ion state, which will denote up and down. And the gate recipe is the following. So we have to tune external force to one of the motional mode frequencies, for example, common mode. So typically people work with common mode. We have to find a force which amplitude depends on an ion state. So we either work with different polarizabilities of the state or something else. And then we end up with the fact that, for example, we can perform the situation that force for spin up ion 1, ion 2 is just opposite to the force to spin down ion 1, ion 2, which is good because then we have very strong situation for two pictures. And the reason is because we can easily excite with this detuned force the common mode, but we generally cannot excite the force for the stretch mode if ions are in different states. So generally we work with only one mode and gain this phase difference which we need. Okay. What we end up with? We end up with the situation that for up state we gain some additional phase. For down state we get basically the same phase, but for up down or down up we gain no additional phase. And again, this gate can be easily converted to a CNOT gate by single qubit operations. So this is a general recipe, and many protocols today are working with this ideology, I would say, because it's what the good is that you do not need to cool the system to the ground vibrational state. It's not necessary. You can work with quite hot ions, and it's fast. So the good thing that this system can be done much faster, this gate can be applied much faster than the Dirac-Zoller gate. Of course, you always sacrifice the fidelity. That's true. So you cannot. So you have to pay always. So it's it doesn't work that you only gain. You also have to pay sometimes. Yeah. And for example, very well known Møllmer-Sørensen gate, which is now maybe their common working horse for all ion-based quantum computers. So Møllmer-Sørensen gate works with it's a bichromatic gate. So you need two laser beams with a detuning from some needed state by delta. So this is blue detuned, red detuned, and you can excite the upper state in two paths, either this path or this path, and depending on realization, on situation. So, for example, I do not have time enough, or it's maybe to go to details because Mørmer-Sørensen gate is quite well known generally, and then I get this geometric phase if we go to the rotating picture, and we end up with a classical Mørmer-Sørensen in two qubit entangled state, which is again can be used as universal gate. So this is the most widespread method. Both a group of Chris Monroe in the U.S. and a group of Reineblatt, they work for their realizations of quantum computers. They use this Mørmer-Sørensen gate. One can work with so-called geometric gate. It's also quite similar to Mørmer-Sørensen gate. When two off-resonant lasers a little bit detuned, there are two different frequencies. You have so-called walking wave or running standing wave. So it's also well known. How to say? So this is running standing wave. So you have a standing wave which runs with a certain velocity in phase, and then depending on the position of ion, you will end up with different interaction because of different state polarizabilities. The good is that there is no electronic transitions, no scattering, but it doesn't work with hyperfine qubits. So this is bad. This works only with optical qubits. This works with hyperfine qubits. Okay, what one can do further. So if we go to very recent ideas, how one can accelerate the situation, because everyone wants to work faster for certain reasons. First, of course, the coherence time of qubits in ion traps can reach minutes, what we're told, but it doesn't mean that it how to say, it's not sacrifice, it guarantees that you can apply gates for 10 minutes, because a lot of sources of other decoherence, of magnetic field fluctuations, heating, different perturbations. So the faster you do the gate, the less you think about all these decoherence issues. And of course, the idea is to work as fast as possible. Approaching, in the case of ions, it's microsecond scale. So today the fastest gates are microsecond scale. Again, of course, you have to pay. So it doesn't work just in one direction. Typically, the faster you walk with gates, the faster the gate, the lower the fidelity. So this is again an issue which one can think to optimize or to work with. But so-called fast gates, which I comment a little bit later, they today reach their fidelity of about 90% at microsecond scale. So which is not so good, which doesn't sound great, but it's maybe some way to improve in future. So the idea is to again work with this additional phase which you can get in phase space. So if you add some kick to the ion, of course you can change typically you can add some energy by not changing the coordinate. It's if you add some force, and then these strange pictures are the manipulations which one can do with ion in the phase space using very short pulses of light, which kicks the ion in some special way by exciting and later de-exciting the vibrational mode, because of course you would like to have no excitation at the end, which means that you have to have that closed trajectory. So this system works. There was a Nature publication of 2019, I think, concerning the fast gates, and now it developing, but people do not know whether it's good or not. So whether it's really good implementation for real systems, or it's just research which is fancy and interesting. But this is the way which one can think about is how the fast train pulses can help accelerating the quantum computation using ions and still have good fidelity. So this is what one can think about in some future. So generally about the hardware, I will not go much into details because it may overload the audience in the evening. I think all of you are already quite tired because it was a session, and I just would like to give some vision of how it's developing today. So if we talk about progress in ion computers over the last years, we see that the 1 qubit gate error reaches about 10 to the minus 4, which is good. Of course, it's, how to say, the best average result, we say as experimentalists, but if it's the best result in some sense, it can be reproduced. This is good, so it reaches good level. If we think about 2 qubit gate error, it again goes quite low to few parts in 10 to the minus 3, which also allows to do already quite complicated algorithms and computations, but with quite small number of qubits. If we talk about entangled qubit number, it also grows. So if again considering ions, so we see that for quantum simulators it reaches about 50, 51, similar to many other systems today. And if we go for universal computers, it sticks between 11 and 13 today. So but it's the best universal quantum computer at the moment, anyway. So if we give an example of one of the best platforms which is implemented in the world. So this is a terbium system, which means that it's Chris Monroe and his team. It's 11 qubits which can be entangled with each other. It's a chain on qubits. It's acousto-optical element which addresses each of ion arbitrary in this chain. This is detection optics, which is again multi-channel, and there are some common beams, which global beams he calls it, which how to say, supports all these operations. The good thing that you can switch any pair of this beam. You can even do it in parallel, so you can address 2 pairs of ions simultaneously, which is good. These are the published numbers, which I just copy-pasted. So the averaged 1 qubit fidelity for single ion is more than 99%. Average 2 qubit fidelity, averaged, which means that because it really is space dependent. So if you go further from the center of ion chain, the fidelity typically goes down, and this is also one of the problems today. So anyway, it's more than 98%, and some very well-known algorithms are implemented today using this platform. It looks nice. I mean, if you look at how it's assembled, so I like it very much because we at Lebedev also worked at compact ion frequency standard, and I understand how it's quite difficult to put everything together that it works. It's not so easy to have not things on the optical table or 2 optical tables, but to have it in one box. It requires some thinking, I would say. And this is the system. This is the chip, which you can see here is of course much more high level and top notch than what we use at the moment. But it's not really, how to say, very difficult technology which is put there. Micromachining is quite challenging anyway. So there was a quantum simulator based on 53 ions reported by the same group recently. So again, there's some regular argumentation what this simulator can do. So it's a modeling of some phase transitions. You can change Hamiltonian interaction between these ions, of tune. I wouldn't say to change, but tune Hamiltonian, and to do some nice tricks with this complex entangled system, and maybe demonstrate at some moment that it's more powerful for some applications that compared to quantum to classical computers. What are the future development? I would say that there are a few things which seduces people today. Of course, one of the key problem is scaling. So this is a problem, and people understand it. There are different approaches. Which people think about is, for example, 2D arrays. It's not so straightforward as it looks like, because I will show it a little bit later. You can really do planar ion traps. So you do not need 3D. It can be done on a chip. But on a chip, you have an ion very close to the surface, which means that you have a heating. And all these nice tricks with 2D or whatever, you need first to solve the problem with heating. There are some, promising reports. For example, this paper, very recent, where people tried to use superconducting chips and superconducting traps, and you see that at 85 Kelvin, the heating rate drastically went down, because it was I don't remember the material, but anyway, but it's not yet reproduced, and it's not clear where it's really, breakthrough, or it just a good it was bad here and it become for some reasons. At the moment, I think Innsbruck team. I think Innsbruck team. Of course, half of the world today work with cryogenic traps, because all these heating effects, they really go down just because of temperature. So they go down. So if you cool down the system, but then you lose advantages of I think it's still advantage of ion traps or neutral atom trap, which I like, because it works at room temperature. You do not need a fridge. You do not need a blue force. It's always nice to disentangled from this technology of low temperature. People think about fast non-adiabatic gates, maybe with femtosecond pulses. People even think about attosecond pulses, but of course it's out of today's technology. But femtosecond can be good, but again, it's a trade-off. And of course, what one needs is some special optics to address ions. Of course, it's not only the single place in the world. So where people do these quantum computers in Austria, they also work on building transportable system with ion trap. Of course, it's quite long, quite old story. So it started like about 10 years ago. Is to work with the planar chips. So you see that this configuration. I have 2 minutes more. So they are planar. If you take a planar chip and apply microwave radiation to two rods, and then you see this quadrupole potential very close to the middle. So it works. You can trap ions close to the surface. It's about 30 microns like that, so it's quite close to the surface. But then you can design arbitrary difficult chips and potentials and so on. And there's a nice artist view, I would say. It's artist view, how one can build a real system. So you can have some buffer, readout, place where you can entangle. You can have ions for sympathetic cooling and so on. But at the moment, I do not see a strong progress in this field, really. So it looks nice, it looks very technological, it looks promising, but again, a lot of technical difficulties which prevents, mostly technical difficulties which prevents from even the problem of swapping physically two ions. It's a huge problem. So if you have two ions, one on the right, second on the left, and you just want to make them that way. It's not quantum swapping, it's just physical swapping. It's easy with two cars on the road, but it's difficult with two ions in a trap. So, okay, a few words about what we are doing. So we will discuss it, as far as I understood, on roundtable today. So if we think about the ideas which we would like to implement in Russia, is that so there is a roadmap to build different platforms, and one of the platforms is ion-based, and the idea is to make the cooperation between Russian Quantum Center, Lebedev Institute, and Skoltech, and to build a system which in 4 years gives us like 50 interacting qubits with a very, how to say, promising at one hand side, but also challenging level of fidelities for these ions. It's not clear how it will work. I mean, this huge goal, but this much smaller goal, which we have at the moment, is to the end of 2022 to have the 2 to 5 qubit system with also quite decent fidelities, and this is already, I think, supported, and that what we have to do in very short time today. This is our team at the moment. Most of the people either work with ions or are connected with people who work with ions, and at Lebedev Institute mostly. And we also, of course, always not need, but we invite people who are motivated and interested and would like to join the team. And thank you for attention. I hope that it wasn't unuseful. Sorry. No.
Thank you for a very interesting lecture. Yeah, I would like to ask, as far as I understood, the atoms in this Pauli trap, they are pretty hot compared to the atoms in like neutral atoms, because neutral atoms, they are like at microkelvins, and this they are around millikelvins. But even for neutral atoms, the Doppler effect is plays a significant role. But what about Doppler-induced pulsar errors here?
So there are two commands. So you can make ions as cold as neutrals by subdoppler cooling, so by the sideband cooling. You can work with sub millikelvin regime, but that's not very important, because you work always in lambda regime. So in lambda regime you have the central carrier which is free of Doppler effect. So all Doppler sidebands appear far detuned from your carrier. So if you just look at lambda regime, what is, so you can address the central Doppler free carrier, I would say.
During your talk, you was speaking about trade-off. So to have something, you have to pay for it. So from the point of view of the Vincenzo criteria, which one is the most expensive one?
So you mean what is again trade-off between what? Because I talked about two trade-offs. So which just again.
Well, I mean from the point of view of the Vincenzo criteria for qubits, which one is the most expensive one? Which was the most crucial in your system?
Crucial. So generally, Of course, everything is hard. So the one of the most difficult and expensive in sense of not money, but in sense of time consuming is to build a good ion trap. So this is one of the first steps to have a low heating rate, to have it very symmetrical. This is quite important. The second issue is it's even difficult because it's more or less equivalent. So and the question is, what is the goal? So if you need to build a 5-qubit computer, I would say recipe is quite straightforward. So you do not have to think about fast gates. You do not have to think about cooling to the ground state. You trap them. You apply Møllmer-Sørensen gate, and you are more or less happy. But as soon as you start thinking about larger number of qubits and increasing the fidelity of operations, at the moment it's really hard for me to say what is more important. Is this number of qubits or I don't know the roadmap. It's kind of research in some sense. So it's hard to answer this question.
So what about the scalability of two-dimensional lattice? Are there some fundamental limits?
First, there are no trap which can stably trap two-dimensional arrays like for neutrals, because for neutrals you build a number of optical tweezers or optical traps, and you have two-dimensional system. For ions, it doesn't work. So there are ideas to build two-dimensional systems, but then you have to individual trap on like a hole in some surface, but it's considered today. But I think there are a lot of difficulties which we meet just because of heating and unharmonicity of potential, because the surface traps, they have also a problem of strong unharmonicity. So this you saw that the potential is quite similar to quadrupole potential. So there are ideas how to trap ions in regular arrays, but I didn't see yet a real, how to say, implementation of this approach. Maybe some playing around, I would say. So it's not yet how to say, finalized.
So faster gates tend to have lower fidelity. Do you think there might be some fundamental uncertainty relation of some kind?
We think about it because the issue is that we talked about it with our students. It's interesting. So with these short pulses, so each short pulse can do some more or less reasonable operation. But then you need another short pulse to correct this operation and to make it, because you excite basically, the shorter the pulse, the more vibrational modes you excite. So you cannot address only one vibrational mode with short pulse in ion chain. Then you can apply another short pulse to correct for this, how to say, nasty things you did with the first pulse. And you can end up with really nice circle, and you can close up most of the vibrational modes, but then you need many pulses. Again, so you have short pulse, but you need to have many of them. So there is some certain uncertainty relation in that sense, because short pulse will excite a lot of vibrational modes at the same moment.
The last one. The last question. So you mentioned about some sort of trade-off between fidelity of 2-qubit operations and operation time, right? So could you give the numbers? Because sometimes you said about 99%, but what is the time operation for this case?
Oh, at the moment, so I would say that typical Møllmer-Sørensen gate works in about, let me remember, about 40-50 microseconds. So this is typical I think time for good fidelity. So it's already close to the top. So it's sub 100 microseconds. So what I remember.
Difference time is about minutes. So our factor is about 10 to the...
No. But of course, this again, it's record numbers. So if you have some magnetic fluctuations in the room, or so, but I cannot guarantee, but I think I'm quite close to what is true. So it's about maybe 50 microseconds. It's in some sense good because you do not need very fast electronics like the guys who work with superconducting. They really need very tough, very fast electronics. Here it's not so critical.
Okay, thank you very much for excellent talk. And so before